So I'd like to welcome everybody out. The Perl track is sponsored by Salt Lake Perlmongers. There's on our poster there, you'll see our URL. We have meetings every second Tuesday, except during Openwest. We skip this month. And we meet in Draper at the Mojo offices under Bluehost. And so we'd like to also thank Bluehost for helping us with that. Salt Lake Perlmongers, we meet every month. We try to discuss things that are somewhat Perl related by some level of abstraction. So join the mailing list, go to the website, join the mailing list. All of the talks from the Perl track will also have links on the mailing list or on the website as well. I gave a talk a few weeks ago and I'm Dave Oswald, by the way. So I gave a talk a few weeks ago at a youth programmers development seminar, and they encouraged us to put up our hashtags so that the students could tweet. And so I invented this hashtag here, Perl RE intro. That's the hashtag for this talk. And then, of course, I just want to plug once again Salt Lake Perlmongers. Meeting in Draper. It's not that long of a haul for people from Orem, people from Salt Lake. We're kind of centrally located. And even if you don't plan on coming to the meetings, join the mailing list so you know what events are coming up. Over the summer, we got to have Damian Conway, thanks to Bluehost. We had like 100 people in attendance at that event. So it's a fun organization to participate in. And who am I? This is another thing they told us that we should do in our student conference, and so I put this up here also. I'm Dave Oswald. I've been playing with computers since I was a little kid, as probably most people in this room have. I studied economics and programming at the U of U. And I'm aspiring to be lazy, impatient, and hubristic. So, right? Which are the three virtues of programmers, of Perl programmers. So our goal today is to learn how to save the world with regular expressions, right? Wait a second. Something's wrong there. Let's backspace. That is not our goal today. You can't save the world with regular expressions. In fact, there are many times when they're completely the inappropriate tool. And so one of the goals today is to, in addition to kind of introducing them and getting into how some of the things like backtracking work, one of the goals is to also identify those times when they are appropriate and when they're not appropriate to be used. Our examples will be in Perl, because it's my talk, and also because Perl gives us a lot of tools. Regular expressions are built right into the syntax of the language. Perl gives us a lot of tools that we can use that are good for displaying and showcasing regular expressions. And also because it doesn't really matter, because Perl compatible regular expressions are all over the place. And so it doesn't matter if you really belong most of the time in the PHP track or whatever other track, you're using Perl's compatible regular expressions, chances are. So now we want to kind of dive into some real kind of low-level, kind of the entry-level stuff first. And I want to kind of fly through the entry-level stuff as quickly as we can. However, I also hope that people will feel comfortable in just stopping me at any time and saying, let's talk about that a little bit more. Because I'm going to act under the assumption that there are people in here that are way beyond me in their capabilities in regular expressions. And that there are some people who maybe are just starting out, and then there are a lot of people probably who have varying degrees of comfort in between. And I probably fall in that category too, varying degrees of comfort. And so stop me at any time and we can talk about what about the topic that we're looking at. But I do want to, we're calling this kind of an introductory class or discussion, so I want to start out with the basics. Regular expressions. Inside of a regular expression, literal characters match literally, except I probably shouldn't have put the ... there because those are not literal characters. But literal characters typically, if it's not what's called a meta character or a meta symbol, then that type of thing matches literally. We have some meta characters. These are mostly structural in their use, although some of them are used for other things. And then metasymbols, which many of them represent classes of characters, although some of them can also represent structural things or even positions within a string, anchors we would call them. And in Perl we use, of course, the operators, the match operator, substitution operator, and we use binding operators to bind our match with a string. And so here's just an example. Just another Perl hacker is our string. That becomes the target of our match. We bind it to our regular expression using the binding operator. And now this is going to say the word match if Perl matches from this string, which it does. We can use some syntactic shortcuts. The it variable, the topic variable, will match implicitly if we don't bind to anything, right? So we're not binding. We're not using that binding operator. We're not specifying an explicit target. We're matching implicitly just by using the match operator. And if we're using our typical leaning toothpicks, we don't even have to put the M to use the match operator. So this is simple stuff. Now, a little bit higher level. DFA versus NFA. Anybody know what kind of engine Perl uses? This is the regular expression engine. Any guesses? Perl uses a type of non-deterministic finite automata engine. It's a type of. It's not a purely, strictly NFA. The alternative types of engines are DFA or hybrid engines that represent both. There's the Go programming language has the EC2 regex library. That's a hybrid engine that spends most of its time kind of in DFA land, and we'll discuss what that means. So, non-deterministic finite automata. Let's start with deterministic. Deterministic finite automata, I can't say that, is what you call a text-directed match. The text, the state machine never backtracks, and so the semantics are much more limited. You never get things like look-behinds. You don't get any kind of backtracking with deterministic finite automata. With non-deterministic finite automata, you get backtracking, which gives a lot more power and flexibility at the cost of possibly going on for an eternity before you ever exclude a match or include a match. So awk, egrep, flex, lex, mysql, and procmail all use deterministic finite automata. It gives them a little bit more of a limited regex language, whereas Emacs, Java, grep, less, more, .NET, Perl compatible regular expressions, Perl, PHP, a lot of the more powerful regex implementations use non-deterministic finite automata. So our focus is going to be on non-deterministic finite automata because it's more interesting, more fun to play with. We tend to use it more places, and it's because what Perl uses mostly. So some basics. Again, literals match literals. This hello literally matches hello here. And it typically is going to match, it will always match, if there were two hellos in here, it would match the first hello, starting on the left. Leftmost, longest is the typical order of operation in matching. Alternation, we're going to go through this quick. Earth or world, it's going to pick this one here and match against world. This one is going to match true, yes, for world. And so alternation, this vertical bar represents two alternates of choice. Metasymbols. So some of the metasymbols match classes of characters. W matches what would be, yeah, go ahead.
On the last slide, what if you had hello in world?
So if I had hello here, yeah, it would, well, for two reasons. It's going to, actually for one reason. If I had hello and then world, it would match the hello first because hello occurs first in the string.
So if you had world or hello, which would you match?
If you had world or hello, it would still pick up the hello because, and we'll walk through that. In fact, let's do that. There's a, no, that's okay. This is one of the things I wanted to try doing. So let's go with hello. Or we wanted to try world and hello.
Yeah.
And now we're just going to say hello world. This is a tool that Damien Conway developed. It's called Regex Debugger. It's available as a module from CPAN, our Regex Debugger. Once you download it and install it, you get a utility called RxRx. And that utility lets you step through the matches as they occur. So, yeah. So here we are, starting here at the beginning. And it's starting by trying to see if it can make world in the pattern match hello. And trying the literal sequence world against H, fail. trying the next alternative, hello, matched. And then if I continue to the end, it took 6 steps for it to finally decide, I guess, that that was the best match or the first match. But anyway, so yeah, it's always going to take the thing that's first in the string when you're using alternation. That's a cool tool, isn't it? Yeah. Go ahead.
So as a potential, I guess, micro-optimization, this also teaches you that if you know which thing is most likely to be matched first, you should put that in the first part of your alternations.
You know, that used to be true, but I'm not sure that it's, I'm not, you might be right, but I'm not sure that it's true now because I think Chromatic implemented, or maybe it was a guy named Demmer PHQ or something like that from Germany, implemented tree optimization, TRIE optimization in the alternation, and so it should be able to find any alternation as quickly. Yeah, it should be able to find any of the alternations just as quickly. So I don't know how he did that and managed to. Anyway, yeah, it's an amazing thing. But yeah. Okay, so literals match literals. There's alternation. Metasymbols. So W matches what we would consider. People used to say, well, it matches words, but no, W also includes the digits 1 through 9, or 0 through 9. It includes underscores, and if you're in a Unicode world, which is kind of the standard after Perl 5.14, then it'll match about 120,000 different characters that would be considered characters that can be used as identifiers. And so you kind of think of it as that's a metasymbol that will match legitimate identifiers under UTF-8. Now we're matching, this one represents space characters except for vertical tab, and except for new line unless you use a modifier. And so hello world, well, we have O and W separated by a space, and that one matches true, yes. Common symbols, W an identifier character, S a space character, dot matches anything except for a new line, and sometimes it'll even match a new line if you use the right modifiers. And D represents a numeric digit. If you ever look, it took me a while to find this in the Perl documentation. Perl RE care class has hundreds, if not maybe 1,000 different character classes. Not all of them represented by metasymbols. Some of them represented by longer bracketed patterns. But there are so many different. It's amazing how many different character classes are available. Now we'll look real quickly at quantifiers. Quantifiers allow atoms to match repeatedly, and so an atom would be, in this case, a single literal character. We're going to match the O repeatedly, and with the plus means we're going to match it 1 or more times. And Perl's regular expression engine is greedy, so it's going to match here O, and return a true. Matched O. The common quantifiers, plus represents 1 or more, asterisk represents 0 or more. A literal number inside of brackets represents exactly that many. If we had put 2 up here, then this regular expression would match 00 right there. 2 to 4, you can specify a minimum and a maximum number of times to match. So that would match, because it's greedy, it would match all 4 there, but it would need at least 2. 2 or more times, if you leave off the number on the right side, that it has to be a minimum of 2 times or more. And if you use just a question mark, then it's 0 or 1 times. There are other types of quantifiers. Reluctant means, that's another way of saying non-greedy. Yeah, non-greedy. So with non-greedy, if you have O plus, then it's going to only match the O, unless maybe I put an anchor afterwards. If I put a G at the end, if I go O plus and then a G, then it's going to pull itself along until, or an N, then it's going to pull itself along until it gets to that N. And we'll look at how it does that in a minute. Some of the other ones, so you can put a question mark after any of them to make them non-greedy, after any of the quantifiers. 1 or more, 0 or more, 1 or more, exactly n times, at least n times. I pulled that graphic out from somewhere else and stuck it in there, and it seemed like the appropriate place to put it. So controlling greed, like I just mentioned, putting a question mark after the quantifier makes it match as minimally as possible. So let's take a look at greedy and non-greedy. We'll go over to the regex debugger again. What am I using here? W plus A. What was it again? Oh, it was a \W. Now this is a greedy match, and so the first thing it's going to try to do, as I start stepping through it, it's going to see that W plus and say, I want to match one identifier character or one word character. That's the letter A, and I'm going to match that as many times as I can. Great, matched. But then that would, if it's just stopped right there, then this regular expression would have to fail because it still needs to match an A, right? So now it's going to try the literal character A, and as you can see, we're already at the end of the string. There's nothing more to work with there. And so it's going to, for a second, fail, and then what's it going to do? It's going to backtrack. Go back, it's going to give up one character. Now it's going to grab that final character for the A part of the match, and now it can succeed. There we go. Took 8 steps. Now let's look at it if I make it non-greedy. Oops. First it's going to try the A, that matches. Now it's going to try the literal A, right there, and that matches at the second position. Is that too small? Should I bump that up larger? It's okay? Yeah. All right. And so instead of being greedy, matching the entire string and then giving one up at the very last moment, it now just matches a single with our quantifier and then pulls itself along to the next A that it needs to match. So there's greedy versus non-greedy. Anchors. Anchors and zero-width assertions. So a zero-width assertion, what is that? It sounds complicated, right? But it's not really all that complicated of a thing. It's some form of an anchor that can match between points, between characters in a string. So here we have the zero-width assertion that says to match at the start of the string or at the start of the line, depending on what semantics you're using. But we're going to, in this expression, starting at the start of the string, that's a zero-width assertion. It doesn't match any specific part of your string, except it just matches this abstract concept that's the first that's the beginning of the string. And here we are matching at the end of the string. Here's an anchor. We're anchoring to the end of the string. So this one can only match if there's a world at the end of the string. This one can only match if there's a world at the beginning of the string. There's not a world at the beginning of the string, and so this one is false. Some of the common assertions that are often used, you see the caret symbol for the beginning of the string. Sometimes that can be coerced into also meaning the beginning of the line. And so that one's a little bit unpredictable depending on what semantics you use for your regular expression. Same with this one here. And so people have begun using \A when they mean the beginning of the string, because that is always, no matter what you do to your regular expression, always the beginning of the string. Really says what you mean. Lowercase z always means the very end of your string, anchoring at the very end of your string. Even if you put a modifier at the end of your regular expression that changes its semantics a little bit. B represents a boundary between word and non-word characters. And remember, word could be a lot of different things, including numbers. So really, you think of it as a boundary between identifier type characters and punctuation type characters, right? Or space. Oops. Okay, grouping. We'll do this one quick. There's 2 types of grouping. First of all, why do you want grouping? One of the reasons why you want grouping is to constrain alternation. Alternation, if I didn't have this parentheses here, then this alternate would be Nathaniel, right? Instead, this alternate is Nathan, and the IEL can apply both to Nathan or to Dan, right? The alternates are Dan or Nathan. And so Daniel can match because I use grouping parentheses to constrain this alternation. If I took off the parentheses, then Daniel could not possibly match because the two alternates would be Dan or Nathaniel. So there we are. There's it failing there. The other form of grouping is grouping that captures, and that would be parentheses without the question mark colon. So the question mark colon represents grouping without capturing, and then just the parentheses represent capturing. It's unfortunate that if you look at Huffman encoding, you would want like the easiest to type thing to be the one that's the most common use case. And I think that grouping is probably more common than grouping and capturing. And yet, by our own laziness, myself included, oftentimes we use this parentheses for grouping, even when we don't need the capturing for semantic reasons. And so try to get yourselves into the habit of using the appropriate parentheses for the appropriate type of, for the appropriate use. So when we use capturing parentheses, we capture into the numeric variables 1, 2, 3, and so on. The first set of parentheses would capture into 1. The second set, if there was, would capture into 2. If they're nested, then you start counting opening brackets or opening parentheses. The first opening, second opening, and so on would populate. Yes, go ahead.
I don't want to jump too far ahead.
No, go ahead.
Are all of the items with the open parenthetical mark and the question mark also non-capturing, the ones that don't have the colon after that?
Well, those are, let's see, if it's open parentheses and then a question mark, no colon, then that would be that's an assertion of some sort, right? I'd have to look up in Perl RE what it is. Anybody remember what kind of an assertion it is?
Well, so, yes, as soon as there's a question mark,
yeah. Yeah, it would not be capturing anyway, but it is an assertion.
That was my question.
Yeah, okay, yeah, it's not capturing. I can't remember specifically what that would be with just the question mark and no colon, but yeah, it would be non-capturing. You'll find yourself referring to Perl RE frequently. Even if you're using just Perl-compatible regular expressions in another language, the Perl documentation is worth learning your way around, because that's, if you look at how regular expressions are documented in some of the other languages that borrow from Perl, they're not as well documented, I don't believe, as the amount of information available within Perl's documentation. So captures capture into the variables 1, 2, and 3. Within the regular expression, you can refer back to a capture group using backslash and the number. So you could capture the first character and then refer back to that same captured character using a back reference. Another thing that was introduced, gosh, I don't remember when it was introduced, maybe Perl 5.8 or maybe Perl 5.10, named captures, probably Perl 5.10. Named captures are great. Because now you no longer have to deal with just numbers and try to count parentheses. How many parentheses am I from the left side of the thing? Now you can give your capture a name. And name, I'm just using name as a proxy for whatever identifier you want to put in there, right? And now you can back reference it within your regular expression with \g and then in braces name, or you can refer to it using the global hash, the plus hash, and then the name of the identifier. That would be how you refer to it outside. Use named captures because you can, just like you don't want to name every variable X, Y, Z, A, B, C. This isn't basic anymore, right? You also don't want to have to keep referring 1, 2, 3. It's much better to use descriptive names in your regular expressions. So here we're using a named capture, capturing from A, B, C, D, E, F, G, H, I. We're capturing exactly 3. And we're using the G modifier. The G modifier will iterate over your input string and match as many times as possible, each time capturing into trio. And so we're going to go through a kind of essentially a loop. Where's my loop? Oh, no, I didn't. Oh, yeah, while. There we are. It's a while loop. While A, B, C, D, while this regular expression can continue to match with the G modifier, we're going to capture into trio these triads of letters, and then we're going to go ahead and print them out. They were captured into trio right there.
Do you have what that output looks like?
What the output looks like? I didn't print it up, but it's going to be A, B, C, D, E, F, G, H, I.
Not the dollar and the plus, okay.
No. Yeah, this is, I'm sorry, this is interpolating the variable into a string in Perl. And so you can put within quotes. It might have been easier to understand if I'd taken the quotes off of here and only put the \n in quotes. But this is, we are indexing into a hash. The hash's name is plus. That's just the name of the hash. It's a special hash. We're getting the index in the hash is called trio. And that trio index refers to each of the captures as you iterate through the string. Does that make sense?
That makes
Yeah,
sense.
good.
I don't remember it, but it makes sense.
The slides will be posted. Let's see. Grouping creates composite atoms. So earlier we saw an atom that was just the letter O, right? And it's not real useful if you can only apply quantifiers to single characters. Here we're grouping E and I, and we're saying we want to quantify E and I together as occurring more than one or more time. And so this string will match EI, EI. Matches EI, EI. There we go. And because it's greedy, it will match as much as possible. It'll match the entire EI, EI. I don't know who those people are. If anybody in this room is related to them, I apologize for stealing your photos off of the internet. Custom character classes. So here we've created a character class of our own. Instead of using \w, which can represent 120,000 different characters, we've created a character class that represents only these two characters. It doesn't matter what order they appear in. We're going to match one character from this string, and it can be either an E or an L. And because we grabbed always the leftmost thing first, we're going to match that E. And we have a quantifier, so we're going to match ELL. The quantifier is going to match as much as possible there. A negated character class would say match anything except for EL. See, the caret symbol signifies, yes, go ahead.
You could have done that same thing with the or.
With the alternation, yeah.
But this is another way to accomplish the same thing.
Yeah, if you have, this is another way to accomplish it. And in many times it's semantically more clear if you just put all the things. The alternation is great if you want to match specific sequences of events, right? Whereas the character classes, it doesn't matter what order things appear within them. It's just going to match a single character, and we're going to repeat that as many times as we can.
It's like sticking the pipe between every single character.
Yeah, exactly, yeah. But one cool thing with character classes is that you can compose character classes of other character metasymbols, right? So I could put \w in here, and then it would match everything that a word character would match, and then I could put something else like a punctuation, and it would match the punctuation and the word characters. So you can compose. Here we're matching everything except for EL. So in this particular case, we're going to match the H, because that is not E or L. And it's the first thing.
Match the L at the end.
Because it matches the leftmost thing, and it's only asking for, it's only the E and L break this into two things that can match, right? It's only going to match the first one, unless I put a G modifier, and then I can iterate through.
Right, the G.
Yeah, the G would then take the E, the H, and then the next time through would match the O.
So the caret goes with the bracket, not with the E.
If the caret is the first thing, then it means negated. But if you want to literally represent a caret symbol, then it has to be anywhere other than the first position.
Everything in the bracket's not.
Everything
Not just
except.
Yeah, everything in the bracket is now inverted to mean the.
It's not E, but not all of it.
Yeah.
It's not E and not L.
That's correct. It's a not for everything in there. And that seems like a limitation, right? But actually, a more modern, I think starting with Perl 5.16 or 5.18, we'll get into it later, you can actually do the equivalent of set theory, where you can take intersections and unions, or you can take this and subtract that from it. So you can make your character classes as complicated as you want, not that you would want to. Hyphens are special within character classes. Hyphens inside of a character class represent ranges. And so now we're representing 2, 3, and 4. Or if we had 2 and 6, it would be 2, 3, 4, 5, 6 that it's representing. If you want to put a literal hyphen, then put it at the end. It's almost always wrong to put A-Z and then lowercase a-z. And the reason that it's almost always wrong is because nowadays we deal in Unicode, and that would preclude people's names that have other things in them, like umlauts or who knows what else, right? Tildes. So nowadays, we almost never would want to use A-Z as a character class, unless you really want to make sure you're only matching ASCII-betical alphabet, right? Okay. Character class ranges in 2014. Oh, there we are. I was anticipating what I was going to talk about. So A through Z only represents exactly A through Z. It won't represent Enya. It won't represent umlaut. It won't represent anything else in Unicode. It contains only 52 possible letters because I'm ignoring case. It's probably better to use the Unicode property alpha. P represents a character class property, Unicode alpha. That would encompass 102,159 alphabetical letters across every language that Unicode can represent. So, hopefully your database can handle that too. Character classes may contain most metasymbols. So I mentioned this earlier. So here's a character class, and I've put word characters, digit characters. That's redundant because digits are already contained in word characters. Space characters and comma. Those are all included in this character class. Everything else would be excluded. And so 1, 2, 3, clap your hands for me. That's a song my son used to sing in preschool. Anyway, 1, 2, 3, clap is what would be matched because we are allowing any word character, any space character. Actually, it would match the whole darn thing. Yeah.
Except you don't have a limit of 12.
I have space in there. I think I meant to put non-space, and then we would stop right there. But
It's the first
Yeah.
character.
yeah,
The 12 under.
yeah. The 12. That's what it is. Yeah, that's why it's constrained. Yeah, there we go. You can always mess yourself up with regular expressions. Keep them as simple as possible. Metasymbols that represent 2 or more code points are illegal inside of character classes usually. What would represent 2 or more code points? \x represents a Unicode grapheme. That's one thing that appears on screen, right? But one thing that appears on screen might consist of up to 3 code points, maybe more code points. I'm not exactly sure. And so \x is illegal. \r represents either CR, either control line feed or line feed, depending on what it matches first, and then throughout the rest of the expression, it'll continue to match that. So it could match 2 things. The carriage return and the line feed, you can't use that in a character class. Dot is literal in character classes. I see that mistake all the time where people use dot inside of a character class thinking it's going to match everything, which I don't really understand why you would do that, but it doesn't. It just matches literal dot inside of a character class. You don't need to backslash it to escape it. It's just a literal dot. And quantifiers and alternation don't exist in character classes. If you want quantifiers and alternation, you do them outside of the character class.
That's inside the square bracket.
Yeah, inside the square brackets. Yeah. Mm-hmm. Yes?
I was going to say, for things like \x or \r, if you want to use those in a character class sort of thing, you could do an alternation outside of your character class.
Yeah, those or the character class, for example. Yeah, probably that would be one way. In fact, \x is really a unique one. It's really the only way in all of Perl to sync yourself up with individual graphemes in Unicode. And so there really is no substitute for using that one, and sometimes you have to use it in alternation. So, okay, so a literal opening bracket has to be escaped with a \. There we are. So here we have a regular expression. We want to match a literal opening bracket, or brace, whatever you call those. We don't want it to be treated like a character class, so we need to \. it. I think it's probably not absolutely necessary to escape the closing one. I just did that for my own peace of mind, but it's probably not necessary. You can \/ escape a lot of different things. If you \/ the metasymbol \w, then now you're representing literally a \/ and a w. You're not representing a metasymbol anymore. \caret no longer signifies the beginning of the string, now just signifies the literal character. Any meta character or metasymbol can be made can be tamed to match its literal thing instead by putting a backslash in front. A quantifier, backslash the quantifier, now it's the literal brace to brace. Same with grouping. Quote meta. I don't know why I pulled up the Larry Wall picture, but just a good place to put it, right? Quote meta. If you know that your string has a bunch of untamed stuff in it, and you intend to try to match that untamed stuff, rather than backslashing your opening brace and your caret symbol, just put a Q, and everything that comes after it until the E will now be escaped as though it's a literal character in your pattern, right? It's no longer special in any way, anything between there. Except for one thing, and that's variable interpolation still occurs. So you could still put a variable in there and it would interpolate out to its value. If you want to escape that, then you have to put a backslash in front of it.
When you do that variable interpolation,
Yeah.
is that probably a different section, but is that treated as literal characters, or is that
It's part of the
there's
pattern.
other characters in
No,
there?
it becomes part of the pattern, actually. Yeah. So you have to be careful if you're taking user input to not just plop it in there. Now, if you have it inside the QE, then it becomes literal characters. Yeah. And the E is redundant if it's going all the way to the end of the regular expression. You can just let it fall off the end without doing the E. It's not going to mess up the rest of your world, right? B matches a word boundary. We talked about that a minute ago. Now we're going to look at other zero-width assertions. And the reason that I mentioned B again is because it's a simple one to kind of look at. B, the backslash B, represents the transition point, the zero-space transition point between what we would consider a word character and what we would consider a punctuation or space character. Right. That's a zero-width assertion. Now here we have other zero-width assertions, but you can put whatever you want in there. It can take up the rest of the string, but it's still, in terms of what is matched and captured, is just that it's still zero. And so, what are we using here? We're using a positive look behind assertion. Here we have the string %a, and we're matching it against any word character as long as there was not a % in front of it, is what we're saying here. And there is a % in front of it. That's a negative assertion. There is a % in front of it, and so this one has to fail, has to be false. Look ahead and look behind assertions are kind of an advanced topic, and I didn't intend to really get into them, but they are something. You could create the B meta character, the B zero-width assertion, by some combination of these building blocks right here, these other assertion building blocks.
Would you mind naming what
Yeah, sure. So this is positive look ahead, negative look ahead, positive look behind, and negative look behind. And you can actually even use quantifiers, so you can make it as wide as you want, and you don't even have to know how wide you're making it in positive look aheads, but not in negative. In look aheads you can use quantifiers. In negatives, they have to represent a literal width. It has to do with the way with a limitation of how regular expressions are compiled. It deals with backtracking. You can't backtrack into something that you don't know the width of. So, okay, avoid leaning toothpick syndrome. This is kind of hard to tell, but that's made out of toothpicks. So, leaning toothpick syndrome. So we have the string USR bin Perl. We want to match that. And so now we've got a slash and a slash and a slash, and it starts getting cluttered and ugly. And so what we've done here is we've used an alternate delimiter to start and end our regular expression. Normally you would start your regular expression with the slash and end it with a slash, right? But look what that turns into. Opening slash, now we need to escape the slash that we're trying to match. Then we have to escape the slash that's in the character class that's negated. And then we have to escape the next slash, and then we have our closing. Leaning toothpick syndrome, it becomes illegible, as if regular expressions could ever possibly be slightly legible. This makes them completely illegible, right? And so by putting the M character there, you can now choose an alternate delimiter, and I just chose a comment symbol. It doesn't matter what you choose. But now I no longer have to escape my slash characters within the regular expression. The next step. So the two big rules. The match that begins the earliest wins. And so I wanted to do this one real quick. We kind of looked at this before. The dragging belly indicates your cat is too fat. Let's do that. You know what? I forgot the opening quote. Yeah.
What did you say this tool is called?
This is called regex debugger, and it's available on CPAN. Linux distros probably have RPMs or whatever for them as well.
You started up by doing RxRx.
Yeah, RxRx starts it.
That's an alias.
Huh?
That's the alias to the longer.
Is it?
I believe so.
Regex debugger is the actual module. RxRx could be an alias to a longer command to start it. Yeah.
It's Perl.
And what pattern do I want to put in there? Fat cat belly your. Okay, so you asked earlier about you mentioned earlier the order of the alternations, and we're going to see it doesn't actually matter that much. Stepping through, first it's going to look at fat. This is Damien's interpretation. First it's going to look at fat. In actuality, it's using tree optimization, which means it's looking at F, C, B, and Y in reality, internally. Yeah, does that make sense? Against the T. And obviously that's not going to match, fails. And we're going to try a cat. That's not going to match. We'll go a bit further along, dragging. Let's continue until it finds something to match on. You can see it's working its way through. And finally it stops on belly. Well, belly's not the first alternative choice. It just happens to be the first one in our string that it could match against. And that's where it's going to stop, right there. Took 166 steps to get there. But that's all implemented in C, so we shouldn't care too much usually. Right, usually. Yeah. So that, and then standard quantifiers are greedy. Let's look at that. Well, we already looked at that, but we'll do it again. And what pattern did I want to do? Oh, yeah, this is a good one. Leave anything off there? Oh, yeah. So, what's going to happen here? Anybody have any idea? It's going to the first part is going to match the entire thing, I think. Let's see what happens, and capture into one. Oh, yeah. See the first grouping here. We've told that we want to match 2 followed by as much as it possibly can match of any character possible. And now it has matched to be or not to be, leaving absolutely nothing for the or not to be part, right? Which doesn't matter because our quantifier here says 0 or more times. So this one capture here is going to capture the entire string. This capture is not going to capture anything. And if you took the time to write this regular expression, you probably didn't intend for that to happen. You probably intended to capture something here as well. You won't. And so how do we fix it? Let's see how I fixed it here. I didn't fix it here, but we can fix it really easily by, let's see. Okay, so, I went through it too fast. You saw it. Okay, so anyway, it captured into 2, just the 2, and it stopped there, and then it moved on. It probably captured the space as well, and then it moved on and captured the rest into the second part.
Wouldn't it have to put the B in the first capture?
Excuse me?
Wouldn't it have to put the B?
No. All it needs to do is get to, we've got all the way to the B, you're right. So it got 2B, and then the space character, and then the second part had to be or not to be. Yeah.
So the question mark makes it not greedy.
Makes it not greedy, so it'll match as minimally as possible. Yeah.
Oh, no.
So minimally as possible would be matching nothing.
No, because that's a good question. Because if you look at this, we've anchored to the literal characters 2. Those have to occur. The quantifier only affects this dot here, which is everything that comes after 2. Right? So the 2 has to match no matter what. We call that an anchor. And so we're now anchored to the start of the string, and then the minimal amount that it can possibly match to make this part work out is the space B space. And that's what this dot star question mark is matching.
So
Actually,
could it match the, sorry, could it match the TO as the first expression and skip the B and match the or not the B?
No, it
Match the space.
it matched TO space B space into here.
Not sure the B.
Excuse me?
Didn't worry about the B because it was minimal.
Yeah. No, but it had to because there is nothing. It drags it all the way out to the OR. The OR is your next anchor.
Regex won't skip characters.
Yeah, it won't.
If we have to tell them to.
It's doing it right now.
Is it?
If you had the AAA at the beginning of the string, it would skip that.
It still analyzes those. It's just
Well, no,
they're not part of the
there could be a
management
bunch of crap. It just means
Probably
that.
still have the star on the or not.
I see what you're saying.
See, now I'm back
One of
to
those is
C
the C right there.
See? It's not going to put anything in the second group.
His debugger is wrong.
No.
No?
No,
Because
you have 2 stars. So the first one,
The second one still doesn't have to happen.
the second one still doesn't have.
That's right, yeah. And so it hasn't, that's why it doesn't happen, is because since this is minimal, it hasn't dragged it along to this point yet. It hasn't dragged the pointer in the string along to that point yet. It doesn't match, and it doesn't have to match, and it quits. Yeah, there you go. Okay, thank you.
The longest rule doesn't apply here because of the quantifier.
Yeah, leftmost applies first, and then longest, and the longest doesn't apply at all because we're using the non-greedy quantifier.
You know, you broke your rule of not
I know.
capturing group when you don't need it.
You're right about that, except I kind of wanted to see what it captured, and then I should have run it myself through the debugger because it turns out I was wrong on what I assumed it would do. So, okay. Backtracking. This is a good one, too. Oops. If these seem goofy, I got them from, some of these examples I got from Mastering Regular Expressions, so we'll blame the book for hot tonic tonight. And I think it's... Okay, let's see what this matches. So obviously the 2 fails. That moves the little pointer along. That fails. Keeps moving along. Then it just backed up, backtracked within the regular expression. And I'm going to let it run through its course. And finally, in 52 steps, it ended up matching night. So first it tries to match the NIC, or the 2 from tonic. But then it doesn't have enough to go. It can't finish out its match. So it backtracks and ends up matching the night, essentially. Forcing greedy quantifiers to give up ground. I already displayed this earlier, and in the interest of time, I went, well, I'll do it again. Why not? Forcing greedy quantifiers to give up ground. So here, as we go through, it tries to match the whole string. But then now I no longer have an optional quantifier on the or not to be, right? That has to match. And so now that we've matched the entire string, we're already at our pointer in the string is already at the end of the string. What has to happen is it has to give up some ground here. And we're going to see how it does that. Very inefficiently, but it does it. See? Little by little it gives up, until it's given up enough for the or not to be to also match. See that? 83 steps, but it did it. So, let's look at another one here. Oh, this is a good one. This is kind of what I wanted to get into, is this all this backtracking stuff. Oh yeah, this is A star. I have a terrible memory. I wish I could just cut and paste these, but. Okay, so A is optional, and then the entire grouping is optional, but B is and B cannot possibly occur, and it can certainly never occur at the end of the string. So it's kind of a messy regular expression, but let's just see what happens. And I'm going to tell it to just go ahead and get started on that. Backtrack, backtrack, back. We can look at it and say this can never possibly match, but it took the engine 295 steps to find that to finally fail. And that's not even a pathological case. Out of control. Let's see. A star, B. So it took 213. Was it 213 this time? 295. Something got worse. Oh, because I put more A's in it. Yeah. If we put a plus symbol after our quantifier, then as soon as it's latched onto, as soon as it gets to the end of matching all these A's, it will never give up ground in this outer grouping, and now it'll never backtrack past the end of those A's, and now it takes like 79 steps to execute. So you've just saved yourself some time. You also need to really make sure you know what you're doing when you do that, or else you run the risk of causing a false negative. But putting the plus sign will take away the backtracking feature of the quantifier. I'm not going to run this example because it would take septillions and septillions of years, and the universe would either expand to no heat or contract to the Big Bang all over again. But this one here, so 64 A's in a row, followed by all these A's quantified, and then the fact that it can still never possibly match because it has to have a B at the end, and there's no B there. This will run until the end of time, as we know it. And you won't have to maintain it because we won't be around, but that one's not going to work. If you put what did we change here? Okay, these parentheses here, the question mark, and then this little symbol here, and then this bracket here, that's a grouping, but it's also a form of putting a plus sign at the end of your quantifier. And now we've limited our total number of iterations to 4,550 by forcing it to no longer backtrack once it works its way through the sequence, to never backtrack again. So, longest leftmost, not necessarily. One self-sufficient matches one self. Let's see. Yeah, one self-sufficient. This is optional. This is optional. Even though self-sufficient is longer, it's going to take the one that's leftmost in the string, and it matches oneself and captures self from right there. So even though you think of quantifiers as being greedy, they still have to start at the leftmost position in the string and work from there. And they only give up if they're forced to give up, as we saw it working its way backwards. So, again, just another example. We're using greedy versus non-greedy. Here, non-greedy, this is a gotcha here. The gotcha is that because even though we're using non-greedy thinking we're going to capture as little as possible, this one is optional, and so it still isn't going to capture what you need to at the end here. So let me move on to the next slide now. 6 more non-deterministic finite automata rules. Matches occur as far left as possible. Alternation has to be left to right precedence. Although, even though it is left to right precedence in the alternation, because of tree optimization, it should not matter as far as time goes, even if you put the most common case at the end. If an assertion doesn't match, backtracking occurs to try higher pecking order assertions. We saw it work its way back. Quantifiers must be satisfied within their permissible range. Each atom matches according to its designated semantics. The golden rule of programming: break the problem into smaller problems. Don't do the big, long, complex regular expressions. Even in my talk, I had one that I fouled up, right? Break them into smaller regular expressions that are easier to understand what they're doing. Break your alternations up even. This can be much, or actually that should be an or, but this can still be much better than alternation because it's less confusing to look at. Short circuiting can actually be another optimization as well. If John is your common case, then put John as the first thing in a short circuit operation, and John will be the first one to be matched. And then when it finds it, it's done. As opposed to with alternation, it might have to work its way through the characters and take longer to get the match. So, yeah, the latter is faster if you live in North America, where John is a common name. Modifiers. We saw G earlier. G lets you iterate through your matches. M alternates the semantics of your some assertions. S alternates what dot represents. And X allows for free-form white space. And I want to skip ahead to that. Free-form white space is something you should be doing in your regular expressions. By putting an X at the end of your regular expression, you now can have white space that is completely insignificant within your regular expression. This is a whole lot more readable than stringing it all out on one line. Here's the G modifier. Each time we match one character in the string, and as we match it, we capture it into one, we print it, string. The G modifier iterates using the while loop over the expression. Here's progressive matching. If you put a \G, then the next match, and use a G here, the next match takes place at the next point within the string. So here we're doing a tic-tac-toe board. I'm running out of time, so I'm not going to explain how it works. I encourage you to look at the slides and look into it. The G assertion says to resume the next portion of your match where you finished the previous portion of your match. So the first time, the first match deals with this part. The second pattern now starts up at the second part, and the third pattern starts up at the third part here because of this G assertion. And we won't have time for extended bracketed character classes, but you can do intersections, unions, subtractions, symmetric difference, and complement all within your character classes. So you can say, you could use minus, and you could say, I want all tie characters except those ones that look like Lao characters, for example, by using a minus sign, symmetric difference, or subtraction. So some people, when confronted with a problem, think, I know, I'll use a regular expression. Now they have two problems. That's a famous quote, right? The same person said, Perl's nature encourages the use of regular expressions almost to the exclusion of other techniques. They are far and away the most obvious, at least to people who don't know any better, way to get from point A to point B. They're not always appropriate. Know your problem. Don't use them to parse HTML. Tom Christiansen wrote an HTML parser with regular expressions, and it actually works. But it's enormous, and it's a terrible beast. And Tom Christiansen wrote it. Does anybody? He could write it. I can't. We can't, right? Maybe one of you can. I don't know. Don't do it. It's not worth it. There's plenty of parsing libraries on CPAN, or whatever language you use. There's parsing libraries. JSON? No. Merlin, that's Randall Schwartz, wrote a JSON parser all entirely in pure regular expression, right? And he posted it on Perl Monks, and he showed it to us in Los Angeles Perl Mongers a couple years ago. It's a terrible beast. Use JSON Tiny. That's a module that I maintain. Use that because you can still embed that. His use case was, well, I needed to be able to embed a regex parser inside of a program, and I don't want to pull in modules. Okay, use JSON Tiny, which rips off Mojo JSON. Because it's embeddable. Use that if you really have that type of a use case. It's maintainable at least. Regexes are for matching patterns. Don't match email addresses. Don't waste your time. The first edition of Mastering Regular Expressions had a giant, several-page long pattern for matching RFC compliant email addresses. It was removed from the second and third editions because it had a bug in it. Don't bother. That's Mastering Regular Expressions. Don't bother. There are modules for that. Tom Christiansen said, it's much, much, much harder than almost anyone ever thinks. You'll eventually reach a point where you've worked harder to affect a solution using regexes than you would using a parsing class. Use them for simple things. This is a famous Stack Overflow rant. Look it up. People have probably seen it. About don't parse HTML or XML or whatever with regular expressions. Use parsing classes. Use pack and unpack and subster if you have fixed width fields. Use CSV libraries. If you have uncomplicated, predictably patterned data, use regular expressions. And then we can stop there. There's some abusive ones. Abigail, anybody know Abigail or know of him? He has a prime number detector that uses regular expressions. That's a total abuse of the engine. He also solved the n queens problem, and there's a node that you can look at using regular expressions. That's not what they're for, but it's fun. That's it. Okay, thank you. Sorry for keeping so long. Thanks, everybody.